Hello, I'm going to be talking today about algebra, and I'm going to be looking at some of the research that's out there on algebra, but I'm also going to be reflecting on my own experiences. I've taught algebra in a number of schools. I've taught in comprehensive schools for most of my career. At the moment, I teach in a selective school. I've worked in primary schools. I've run the primary maths hub, and at the moment I teach a lot of further maths. And I think I've seen algebra in kind of all the ways that it's displayed in a school context. And I've seen lots of textbooks, I've used lots of resources, I've tried lots of things. And I think I've developed some very strong feelings about things that are useful, things that are effective, and things that are maybe not as effective. And I'm going to share some of those with you today and try and back them up with some research that I've read over the last few months on the topic. So in 1982, a famous report, the Cockcroft report, was written, and it was looking to change the way teaching was happening at that time, and it did revolutionise an awful lot and created a lot of text and a lot of controversy. One paragraph, which is 201, not the famous 243, which is on the board at the moment, noted that this branch, that's algebra, caused the most anxiety, and recent stage reports confirm that algebra continues to be a cause for concern for most students. And then the famous paragraph 243, mathematics teaching at all levels should include opportunities for discussion between teacher and students and between students and themselves, appropriate practical work, problem solving, including the application of mathematics to everyday situations, and investigational work. And this brought about quite a change to where teaching was and what was happening in maths lessons at the time. And lots of things since the Cockcroft report have happened. We had the national curriculum in 1998. GCSEs was 1988. That's when the A to U, which was linear then. Before then it was O-levels and CSEs, which are quite different. There was much more split between academic and vocational classifications of students that were made then. In 1994, there was the introduction of A-star to try and show that some students really had an aptitude beyond A and could excel. Then 1996 was the national numeracy strategy. And since then, things have changed. They've changed every few years, and I've seen this through my own teaching. We've had a 3-tier system at one point with foundation, intermediate, higher, and then a 2-tier system. The linear and modular systems, which used to be there. Coursework was there at one point. There was an algebra coursework and a data handling coursework, and then coursework was gone. Functional maths was introduced in 2010. And we've had the recent 2017 new grades 1 to 9, with 9 being above the A-star that was previously there. So the purpose of what I want to talk about today isn't so much about me saying which bits I agree with, which bits I don't agree with, which bits I've liked and which bits I haven't liked. I don't think I'm a person to judge, and I don't think there's any real benefits in doing that. But there are observations that can be made. One of them being that there's been a perpetual state of discontent with how maths has been taught, hence the need for changes regularly to try and improve things. According to Tony Gardner, the Cockcroft report sets its initial sights at a more realistic level by starting out from the very basic notion that numerate is being able to perform basic arithmetic operations. Standard written algorithms were widely deemed to be optional. That's things like long multiplication, long division. Different methods came in for multiplying, different methods for adding, ways to try and give students options and different ways of doing things, perhaps to add understanding. Simple word problems, Garner says, and multi-step exercises were neglected. Decimal arithmetic was delegated to the calculator, and fractions were seen to be outmoded. Euclidean geometry, proportion, and algebra were viewed as beyond most pupils, and the freed curriculum time was absorbed by such novelties as data handling. You can see Gardner didn't have a very high opinion really of some of the changes that have come about in time, but they came about in order to try and achieve a purpose. We can't forget that. And I think the new GCSE has taken a step back towards some of those things. You can see the increase on geometry and ratio and algebra, and the expectation that students on the foundation tier are also having to deal with those same concepts and being. So here is a problem. 12y minus 10 is equal to 6y at 32. And in these tests, they were looking at how England compares to other countries at solving problems, and problems like this. So I'll give you a moment just to think in your head, what do you think the international average was in 1999, and what do you think the average for England was in the number of students who could solve this? So you can see we're far below the international average. And for me, this is quite surprising because this isn't a contextualized, difficult problem. This is a routine procedure. And it's of my thinking that we should try and get as many students as who are able to be able to do routine procedures and processes, because if you can't do routine procedures and processes, how can you build on that to generalize into more contextual problems or things that involve multiple steps? So coming back to the problem that caused such issues in 1999, that so many students from our country couldn't solve, what would we guide students to do as their first step? Or would we just let students choose to do whatever they want? Would we say you could add 10 to both sides, you could take 32 from both sides, you could take 12y from both sides? They're all good ways to solve it. Or do we need to guide them in a specific way and get them to practice that specific way time and time again until they become proficient, and then get them to understand why that specific way is indeed the best way? Gardner says preoccupation of mastery of traditional basic content, such as solving basic equations, has given way to an emphasis on understanding. Should mathematics classrooms be guided by discovery, by children's own reasons, and by investigation? Or is there a place where, after brief discussion, we show students how to do it and how to do it best, and then give them opportunity to practice repeatedly until they master these basic skills? Gardner says, a touching faith in students' own methods, even where this hinders their progress, a distaste for doing groundwork of establishing robust fluency in basic technique. He observes there's a confusion between algebra and subjective pattern spotting, and the view that abstraction is off-putting and can be avoided. And related to algebra, but on another slightly tangential issue, he mentions that claims that it's unnatural not to encourage the use of calculators. And I can see this, especially at A-level now, students solving everything on a calculator, students unable to work through surd problems, even unable to really nicely solve quadratic equations because they go to their calculator immediately. Mental methods, which are central in the primary curriculum that students can solve really quickly, things are just being discarded, and students are doing basic times table work on their calculator. And we have moved in our use of technology to a place of taking away basic maths and basic good mathematical processes. To quote Jennings, someone a little different this time, substantial research projects seem to have been largely ignored by curriculum developers and text authors. And I can personally say I've tried multiple textbooks, and they all have really nice things, really nice ways of explaining things, but no book that I've ever found has taught algebra specifically in a way that starts at the beginning and moves to the end. You have to take bits from different books or make up your own bits. There doesn't seem to be something really comprehensive that works in the way that I want it to for the students in my school. Maybe somebody else has found something that works perfectly for the students in their school. I remember being a very young teacher, every week we would take our students out to do an investigation, an algebra investigation, and they would do their little sums and look for patterns and write them in a table. And then if we were lucky at the end of the table, they'd come up with a formula. And we were all amazed that they could do this formula and praising of them, but were they really any better at algebra than students now? And did that really prepare them for what they need and what their true potential for being able to solve equations and work into abstraction was? And I would argue no. I would argue we wasted an awful lot of time allowing students to explore things and investigate themselves, and simple basic processes did not become concrete. We have a new GCSE and a new A-level, and they are both more demanding. And we have to now consider whether our curriculum planning, our textbooks, our methods of delivery are suitable to prepare students for this set of GCSEs and this set of A-level exams. There are some realities behind this. And quoting Gardner again, but I've got some quotes then that will follow from Jennings and Dunn. Mathematics for many students and mathematics teaching is by its very nature hard. Mathematics is by its very nature for some students hard. I think we have to agree with that. There is no cheap alternative to facing the fact that abstraction is a crucial part of elementary mathematics, almost from the outset. From the very beginning, we have to get students to generalize, by repetition, to become fluent in a simple process, and only then can they start to apply that process. This is from Jennings and Dunn, 1996, The Nature of Mathematics. We have to argue that the essence of maths is symbolism, and this essence is algebra, and that school mathematics needs to put algebra in central position. If we are to be successful in placing this emphasis on algebra, we need to consider carefully the difficulties that children have in learning the subject and find ways to overcome these difficulties. I do not believe that we should adopt the view that because something is difficult, we should remove it from the curriculum, as seems to have been the case with curriculum developers in recent years. Instead, we should take seriously the recommendations in the research, and rather than reduce the complexity of mathematical symbolism, we should induct learners through principled activities that maintain its complexity. Key Stage 3 has to start from pupils' experience at Key Stage 2, but this prior experience needs to be revisited and developed in fresh ways. So I'm going to start by talking about our curriculum at Queen Mary's High School, how it's been constructed and why. Firstly, I'm not trying to sell it as a curriculum that will suit all students in all schools. It's right for us. I also want to stress that when we built this up at the very beginning of when the new GCSE curriculum plans were being made, lots of the work we did that wasn't number and algebra in year 7 was pushed to later on in the school. Most of our year 7 curriculum focuses on number and algebra, and even topics that come up such as geometry, angles and things, we try and put an algebra slant on so that students are using algebra all the time, they're practicing it and they're becoming fluent in it. We're not avoiding it, we're embracing every topic and trying to really push it to the forefront. So I've listed here what our first unit is. This is done very early in the first term. It's just after we do a number unit, and in the number unit we certainly want to make sure that the order of operations and things is secure and the use of brackets is good, because you can't really move on to algebra unless that number work is consistent. Now, all of the slides and all of the resources I've got here I can share with anyone who needs, and my email address is at the end, so do get in touch if you need anything. But what is algebra? That's the question, and that's what we talk about, and we really try and put it into a language. Students know languages at this point. They know how to translate from, say, English to French and vice versa, and we want them to be able to translate from algebra back to English. And so we give them the rules, only 3 rules at this point: the use of no multiplication sign, numbers before letters, and how we write the division sign with a horizontal vinculum, and really getting them to set that out. Obviously, if they don't use 2 lines and they don't use a horizontal vinculum, when they move on to algebraic fractions later, they'll have all kinds of difficulties. So at this stage, we talk about things like how we write different letters, our choice of letters when we do algebra, things like we can't interchange between capital letters and non-capital letters. We don't use O's and L's very often because they can look like numbers, how we do our S's, and also how we write our X's, so they don't look like multiplication signs, and trying to get students from the very beginning, before we start doing anything complicated with algebra, just to write it effectively and to understand why we do it. And there are rules, like at the bottom there I've got AX plus B, and explain that it's the same as B plus AX, and show them why they're the same, put some numbers in instead, and convince students that it's absolutely fine. I'm always surprised at different points where students mark their own work, and they mark their own work wrong because the answer in the back of the book has numbers in a different order or letters in a different order than what they've got in their book, so they just assume it's wrong. And trying to dispel those things very early, and potentially going slowly and giving it the time it needs. This is exactly where we start. We've got a problem. For all algebra, we start off with, I think of a number. I times by 7, I add 8, and students usually can write an expression for this, and typically mini whiteboards are a very good way for students to write this and for the teacher to see who can do it, who can't do it. The order is often somewhere where students get wrong. But again, giving this the time, giving lots of repetition in translating between this general case, this is our general case, that I think of a number. At some point, that number will be an angle, but not now. This example's a very good one because students won't take care in how they write it, and explaining that vinculum, that divide sign, acts as a bracket. And that relates back to our previous module where we did order of operations, showing them that we take that apart and we do something to it all. So typically then we've introduced it to the students, we've discussed it, we've seen on some whiteboards, they might do some of their own work, and here's some more questions, and you can kind of see the increased difficulty coming. If you think of the last one, I think of a number, I multiply it by 4, I subtract 5 lots of a different number. So we're looking at introducing different letters, and how we can algebraize that and how we can translate back and forward. I've got multiple sheets, and before I came, this was a curriculum I inherited, really, the first stages of teaching algebra when I came as curriculum leader, and I was amazed on how long we spent getting students fluent at doing these things. And as you look at this worksheet, you can see they link them together very nicely, and they're given the English and they're given the algebra. But again, there's so much richness for discussion. You can see J on the right column, 3n all squared, and then n 3y squared. And why are those two things different? And m, I think of a number, I times it by 7, and I divide it by a different number. And then move on to something like this, where they have to just, it's not a case of linking, they have to find the algebra for themselves. And again, to pick some of the latter ones out, pick number O, I think of a number, I multiply by 3, then this result is multiplied by itself. So the use of brackets, the use of indices, all together, very, very important. You can see another one here, and again these things would be put into the homeworks of students, so they'd be completing them at home, and really thinking and kind of immersing themselves in this language. And again, you'll notice at the moment we've not changed our context of the algebra. It's all been, I think of a number problems. We've not moved to accelerate that into different contexts. We want them to become really good at reading and writing algebra, and to understand what it means, and to understand what it means in as abstract context as we can. So again, another homework exercise here, some of them at the top to write algebra for those, and the bottom ones to write them back as words. And again, if we look at the very last one of the bottom, I think of a number, I add 2, and I divide this into 3. Whenever a learner solves a problem, there is available the question, what is the method that was used? Which is intimately tied up with the question, what can be changed about the problem and still the same technique or method will work? Or what is the class of problems which can be solved similarly? So here is a sheet, just a very short matching exercise, but it shows that next step. So when we've become confident in the language of algebra and the simple rules of algebra and how to write things down, having formal definitions, not so much learnt by rote, but really embedded in a student's understanding, becomes very important. And here in the context, I mean specifically, what is an equation, what is an expression, what is an identity, and what is a formula. I'm not advocating the definitions that I've put here because it needs to be what's right for the students that we're teaching, but how many times have we seen expressions in exams, quadratic expressions that students then go on to solve? And the idea of an identity is quite weak in most students' understanding anyway, and when we go on to proof at a later date, we need that idea to be really, really clear. So these would typically be notes we'd give the students, and we'd ask students a set of questions as to what they are, and to get students familiar with some formulas in different contexts as well, to try and take as many formulas as we can from their own understanding and develop them on a little bit further. But maths is based on definitions, and if our definitions are weak, if what we understand something is weak, we will make mistakes and we won't understand what we're talking about when we're trying to communicate mathematically. And examples of this we see as students mixing up LCM and HCF because they don't know what those letters stand for and they don't know what those words stand for and what they mean. Even as to understanding things like why 1 isn't a prime number. And it's because we need a good definition of what a prime number is. When students are solving Pythagoras' theorem, they've learnt something like a squared plus b squared is c squared, rather than in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. And they haven't got the definition, so therefore they don't identify the hypotenuse, or they don't notice it needs to be a right-angled triangle. And again, the examples of this go onward and onward and onward up until A level. Questions where it says show or prove, and questions where it says work out, and students don't adopt the right strategies for those questions. So right in year 7, we try and get students to have the language correct, to know the definitions, if not be able to cite them, then just to be able to categorize, this is an equation because, this is an expression because, this is an identity because. And that's the kind of discussion that we want and we want to develop. So we've started now building expressions. The next stage is substitution. And the type of exercise I've got here is a very nice way to build substitutions up. And typically we would give students examples like this where they put the numbers in, obviously without a calculator, and they build up and build up and build up, and you can see the ones around the peripheral outside are the ones we're trying to get to. And we want our students in year 7 to be really confident in solving substitutions like this, showing every step of their working and understanding what they're doing. And to get them there, they need that scaffolding. And notably, students need different amounts of scaffolding. You'll see this sheet here has no scaffolding in the last 2 questions, but quite a lot of scaffolding earlier on. This is a game that I sometimes give students to play that they like, and again it uses more just substituting numbers into little expressions to practice those skills. I've got a top trumps game that I play with students where they have their different attributes and they need to substitute numbers I give them. So I feel very strongly that students need to see algebra being modelled for them. They need to see teachers doing it, and they need to be confident that that's the way that they're going to set their work out. And if they set their work out in a way that isn't going to help them develop, they need to be corrected and they need to do it again. So if I was modelling this on the board, I would firstly write 3p plus 2, and then I would make my substitution. 3 times 4, 2. So I've gone from an algebra problem to a number problem. Within my algebra, I don't have any multiplication signs and things, but now I can have multiplication signs. Times 6. We underline our answer, which is consistent presentation at Queen Mary's, and using a ruler we would underline our whole question before we move on to the next one. And it's times like these where you might want to discuss with the students that writing 3 times 6 is another way of writing it and perfectly correct. And 3.6 is actually mathematically correct, but not the notation we're going to encourage because of confusion with decimal places. But again, talking about those things isn't a bad thing, and showing them this is how I want your work to look in year 7 at that time, and being consistent both yourself and as a department in how that's going to be done. So the previous one was an expression where we substituted numbers in. This one is a formula. A person gets P pounds for every H hours they work. The relationship can be expressed using the formula. How much do they earn if they work 10 hours? So we put our number in. And we can now put our multiplication symbol. And again, if it's the consistent method of the department to use a bracket, that's absolutely fine. But discuss that using our order of operations. Now, if we've got a contextual problem, we want to answer with a written statement. So I would say here, if they work 10 hours, they get £250. By writing a sentence, I can check that my answer is sensible. I can also include things like units. As we go through the school, especially at A-level mechanics as example, we have to make sure students are putting a comment at the end of questions, talking about whether something's a vector, talking about their rounding and how they've chosen their numbers of significant figures to use, and of course units. So why not get them in that practice in year 7 and at least model how it should be done throughout the school for them. So we're moving on now to solving equations, and we want students to have a consistent approach and the department to have a consistent approach so that everyone is singing from the same hymn book, as it were, and there's no inconsistency with how students work. So we read this. I think of a number, I times by 2, I add 3, the answer's 11. So we think to ourselves, how can we unravel that using inverse operations? Sometimes inverse operations need to be discussed slightly in advance or during this problem. What's the opposite of add 3? What's the opposite of times by 2? So anyway, think of a number, times by 2, add 3, the answer is 11. The opposite of adding 3 is subtracting 3. So we have 2x is equal to 8. The department will need a policy on whether or not you do take 3 from both sides. Again, we choose not to adopt that, but if you are going to adopt that, you have to take that through then when you change subjects of formulas and things like that, and the same method can be done. The reason why we choose not to adopt that is I want a method that students can become very good at, and that will take them right the way through A-level and through life. And I don't think students beyond a certain stage need to be writing that on both sides. So we read this, I think of a number times by 2 and add 8. So I'm going to divide both sides by 2. Division is the only operation of the 4 of them that I do always do, and that's because it limits the number of silly mistakes that students make. I spent the majority of my teaching career not doing this, and I saw other people doing it and was always a bit sceptical until one year I had a year 11 class, and this was the question in the exam, and 4 people wrote down the answer of 2. And then I knew that what I had been insisting that they do and the method that I'd taken them through hadn't been good enough to limit that number of students making the same mistake, and students do make that mistake very often. So if we force students all the time when they're solving an equation to do division, it forces them to use fractions, forces them to consider that. So I'm a very big advocate of that. Coming back to the question we've just done, we also want to model for students checking answers, and it does take practice to do because we become quite accurate at doing it correctly, but we've got our answer of 4, so we check it works. We don't necessarily need to write it, but 2 times 4 add 3 is the answer 11. And some students will need to write that down. 2 times 4 add 3, and they will need to check it. But getting students to check solutions is fundamental to making sure they limit silly mistakes and they can be confident in what they're doing. Again, trying to give them as much richness in different types of equation, not just the same type repeated time and time again. So here I think of a number times by 6, take away 8, the answer is 7. So we've got 15 is 6x. I think of a number times by 6, the answer is 15. Opposite of times by 6 is divide by 6. So now we have x is equal to 15 over 6. We can simplify that. 3 is the highest common factor. So we've got 5 over 2. And again, having a departmental policy, but perhaps more important, just a discussion with the students about what we do with this. Do we write it as x is 5 over 2? Do we need to? Do we write it as a mixed number? Do we write it as a decimal? And again, consistency, I think, is the most important thing with that. I would very much like them to not be writing it as a decimal ever, and I think that's the only thing that I would feel absolutely strongly with. Quite often when we've got inequalities, if the unknown is on our right side, we do try and rewrite it and interpret it, so I do have a tendency to do that. But again, it's not something I feel very, very strongly about. We've got an interesting one here though, because do we check our answer? And that is again a conversation to have with the students. 2.5? Yeah, I think I can check that. 6 times 2.5, well, 4 lots of 2.5 is 10, so that's 15. 15 take away 8 is 7, and I can be confident that it's correct. We will get answers here where the checking becomes harder than actually redoing the question, and again discussing those cases, but never just missing out the check, never just skipping it as if it's not important. Giving it the time that it deserves is very, very important. So another question here, and I've chosen this one because I think this is the right time to do this question. The class have not been taught with me yet how to expand a single bracket, so therefore no one would think of expanding a single bracket. They will think, I think of a number, take away 2, times by 3, the answer is 24, so we divide both sides by 3. X minus 2 is equal to 8. I think of a number, take away 2, the answer is 8. Now, again, I'm a very big advocate in doing expanding a bracket after they've become proficient in this, because if they had a problem like 19, 17x plus 2 is equal to 38, we certainly wouldn't want students just expanding the bracket and trying to solve it. We want students to be at the right place where they can make that decision. So later on in Year 7, we do have a unit where we have questions like this mixed with questions like the one like 3x plus 5 is equal to 7, where we would encourage them to expand the bracket first, and making those decisions takes a little bit more maturity than where we are just now. So just solving equations like that. So again, questions like this I think really are nice because students in Year 7 in particular will make a mistake going from x plus 3 is minus 14 to this, and that's why these questions have to be chosen as examples to be modelled and to be discussed. And if students are in the habit of checking, they will limit those mistakes from an early time. Minus 17 add 3 is minus 14, divide by 7 is negative 2. And whereas students who don't check and who just get away with not checking repeatedly will make those mistakes, and they'll start making them early, and they'll end up making them throughout their mathematical lives. I think of a number, divide by 3, take 5 times by 2, the answer is 6. Divide both sides by 2. X divide by 3 minus 5 is equal to minus 3. You might think again it's strange that I keep doing that division operation all the time, but I continue that into A level. I've become in a habit of doing it now. I'm teaching further maths in year 13, I still do it. I always model from year 7 to year 13 the same processes that just get repeated by the students, and they get stronger and stronger at doing them. I think of a number, divide by 3, take away 5. The answer is minus 3. X is equal to 6. I can check that. 6 over 3 is 2. Minus 5 is minus 3 times by 2 is minus 6. And again, I've often seen in year 7, most textbooks don't really go into questions of this many steps and this many operations. Students would immediately be accelerated onto something like double-sided equations. But we want students to be able to do multiple steps to become very skillful at solving equations of this sort before we accelerate them onto something new. So I think of a number, times by 4, take away 3, divide by 5, add 2, times by 2, add 3, the answer is 17. So again, I've already mentioned differentiation a little bit, but I kind of want to push that these are not problems at this point in year 7 we would be doing. Double-sided equations, not yet. Questions where the unknown, even though it's obvious the answer's 3, even though it's obvious here that the answer's 4, we don't have a suitable method yet, and we certainly would want students to be solving that as a first step, not dividing by -2. So we differentiate by using the same process by adding steps or by adding conceptual ideas. The idea of having 2 solutions in the first one, the idea of cubed rooting a negative number, and just more generality. But we don't want to move students on to new topics. We want to try and explore topics, and that's very much adapted to the national curriculum as well, which is pushing for breadth rather than acceleration. And again, we do need to differentiate, and possibly the last few questions will be the differentiation that we give, which you can see is actually changing the subject of a formula. But students who grasp the topic confidently tend not to have a big problem with that. So we've done formulas and we've done solving equations, and this is our final bit in this year 7 unit. We've got an equation, a familiar one from A level, and we do like to expose students to as many different formulas as they can, although we won't emphasise and talk lots about what all the different letters mean. But this idea that each of the letters here stands for something is really good. And it's really good enrichment for students to understand as well what formulas are and what these concepts are. So we have our formula, and we will put our letters into the formula. We'll put 100 is equal to U. So our U is what our unknown is. Put a letter in. Now ideally I would like to put that 2 in front, and we'll talk that we could just put it in front, or I can put it there, that's absolutely fine. Plus half, the acceleration is 30. We've got here 2 squared. Okay. Maybe we talk a bit about why I haven't chosen to put time signs in here. And the reason for that is that we actually have an equation, and in equations we don't put time signs. We tolerated it when we substituted letters into numbers into expressions earlier because we were moving to a number problem, but we don't want any multiplication signs in here. But if we did, we wouldn't get marks lost, and for year 7 in particular, that would be reassuring. We want to simplify 2u, so that's 15 times 4 is 60. Take away 60, divide by 2, u is equal to 20. This is a contextual problem. What is u? A car's starting velocity u. So the car's starting velocity is 20 meters per second. Again, at this point I wouldn't stress about direction or anything like that, but it's just getting used to using formulas, and I suppose this would be at the very top end of where we would get in this unit. We've done substitution, we've done equations, we now want to substitute into a formula and rearrange that, and all the work we've been doing about I think of a number and unravelling it has been building up to this. So that is our first unit, and that's the only unit I'm really going to kind of show you all the resources and all the different types of questions we do. But I will just go through the rest of our Year 7 curriculum and Year 8 curriculum for algebra, in case it's helpful for any curriculum planning or ideas of just how pedagogy works for it. So in Year 7 we would cover decimals and negative numbers and fractions and geometry, and we would look to use as much algebra in those topics as we can. So substituting negatives into formulas, into expressions, and evaluating them. When we do our geometry, having the angles as being algebraic. This is from our geometry unit. Obviously we would set it out with correct comments and the correct layout to be in line with the geometry work. Trying to make simple proofs here. So the exterior of a triangle is equal to the sum of the other two interior angles. We can start to generalize, we can start to bring proof into this, and that's only because we have secure algebra. So we would obviously be wanting to be quite confident in our geometry in Year 7 as well, but being able to prove results, being able to reason why they're the case, why are angles in a triangle adding up to 180, and having that confidence with the algebra to be able to get to that result is highly desirable, and again that time invested earlier on in the algebra, the extra time, really needs to precede this, because we want students to be able to reason algebraically in their geometry unit. Then later on in Year 7, so we're talking now in the latter part of the second term, we do collecting like terms, expanding a simple bracket, and just more kind of rules and confidence. So perhaps things like this, 6x add 8 over 2, and discussing why that is the result of 3x add 4. If we did have 6x and we broke one of our rules of algebra and we put a times sign in, but why wouldn't that be a similar result? Why wouldn't that be 3x times by 4? And talking about those things when the time is right, I suppose, and the maturity is slightly higher. Solve equations that involve a bracket. I've already discussed that a little bit, but if we've got 3x plus 5 is equal to 10, we wouldn't want them to do, I think of a number, add 5 times by 3, the answer is 10, and unravel it. We'd want that, and we'd want them to be able to justify why that would be the case. And obviously at this point we'd be more confident with our negative numbers as well, so we can extend and we can revisit. Later on in year 7, equations with the unknown on both sides, when we have things like 3x add 8 is equal to 7x minus 6, and we would really insist here that students subtract the smallest x term from both sides, not take away 7x from both sides, and really make sure that they're confident, they're not making a decision as to what to do, that they can do this every time repetitively. We then have 2 final units in year 7. One of them comes back to sequences by structure, and that's a very interesting one. It's trying to make algebraic conclusions through looking at the shapes in a sequence and looking at how a shape develops, rather than just by counting the number of terms, but trying to see what kind of shapes develop in a quadratic way, which kind of shapes develop in a linear fashion. I suppose this is more of the exploration and the generalization, but it's notable sequences by structure is happening after we can find the nth term of a simple sequence. Okay, and after simple quadratic sequences are secure, not before. And often you'll see in textbooks they're working the other way. They're trying to give you a pattern first of all, and then get students to generalize from the pattern and try and develop the algebra from there. But we really want the algebra to be concrete first, so that then we can start contextualizing, and the time taken to put it in the context is much quicker, and we can go to much more complicated. And we finish year 7 off with an algebra investigation. This is at the end, when it's secure, when they're able to explore, when they know results. It's not the other way round. Into year 8, and this is a list of all our year 8 topics really. We take our graphs on more, we expand pairs of brackets, we factorize into single brackets, we change subjects of formulas, we look at simultaneous equations, we solve equations such as this. By adding 3x to both sides, which is much neater than taking 5 away and then dividing by -3. And we look at simple algebraic fractions like 3 over x is equal to 7 over 2. Notice how the method for doing a problem like this, we can't do it by unravelling the layers. We have to take that step of cross multiplication. So some final comments. So one of them will come from Tony Gardner's work, and it's that in countries with strict social expectations and carefully structured teaching, large numbers of students master basic methods rather well. In countries with a more relaxed social structure, students may say they like mathematics, but they don't perform basic procedures nearly as well. And it's an observation, but we can't really compare ourselves with countries where the social norms differ in the way students have been taught. But there's also an inference there that liking something and being good at it are 2 different things, and we should be challenged as teachers to make our teaching effective, making our teaching engaging. But the main purpose of it is not to create happiness and joy. It's not to create pleasure. It's to be engaging and to be purposeful. But if we try and make our teaching algebra very, very fun, very, very investigational all the time, we may get students saying that they really, really like it, but it may have very little effect on their outcomes and them improving their algebra. So that's an interesting observation, and that's from Gardner. And going back to Mason, he gives a warning about people's first experience of algebra that can be very, very detrimental to their understanding, and that's the idea that A equals apples, B equals bananas, rather than A equals the number of apples and B equals the number of bananas. The idea that letters stand for numbers, and if you've not had that idea from the very beginning, perhaps collecting like terms has been done with bags of shopping and things like that, misconceptions are there that need to be corrected. And I've left a final thought on the slide. By treating algebraic thinking as a natural consequence, the use of learner's power, algebra can be an intellectual obstacle of adolescence. It is a natural birthright of all human beings. Whether or not you agree or disagree with that, I will leave that up to you. If anything that I've done brings you any want to write a comment, I'd very much value any feedback, or if any of the resources I've used you think might be useful, or if there's any points you want me to elaborate on, I'm more than happy to engage with that. And good luck with your teaching algebra.